We've seen the reaction of alkenes with Br2 or Br2 with another nucleophile. So how about we look at it with some other molecules? So the simplest one is to take, rather than Br2, we're going to look at HBr, or as an example, H3O+. And what we need to think about first is, what's the electrophile and what's the nucleophile in each of those reactions. Now we know from the previous reaction mechanism that the alkene can act as a nucleophile, so we know that this double bond has got high density of electrons and therefore can donate those electrons as a nucleophile. And then in this case we're looking at HBr or H3O+, in which we need a species which is lacking electrons to be our electrophile. So if we think of the structure of HBr, we would have the hydrogen would be very delta positive, the bromine would be delta negative. We know that the bromine is more electronegative than the hydrogen, it's going to pull the electrons away. We know that HBr, just like HCl, is a form of acid, so it's going to provide a H+ source. And we can see the same thing here. If we think about H3O+, what that really means is it's water with some protons around. So in these instances, the alkene will act as our nucleophile, and the hydrogen, the proton, will behave as the electrophile. Okay, so let's think about what that would do then. So we're going to have our double bond, which is going to act as our nucleophile, and we know that what we're looking at is having some sort of H+, either as HBr or as H2O+. So both of these give us effectively a source of H+. So let's just simplify by saying, okay, we recognise if we have something like HBr or H3O+, what that really means is we have a source of H+. So we're going to use our alkene as our nucleophile, and we're going to attack the electrophile. Just very similar to what happened with the Br2 example. So again, we've broken that double bond. Both of the electrons have gone to form a new CH bond in this case, which means that the carbon that doesn't have the hydrogen attached to it now will have a positive charge. So we've formed a carbocation there. And just like with the previous example, in that case, we used the extra electrons from the bromine to form the bromonium ion. In this case, hydrogen doesn't have any electrons that it can spare, so therefore we don't form that the equivalent of a bromonium ion. So the carbocation stays there, and that's what can then be attacked by our nucleophile. So for example, if it was Br-, the Br- would attack, neutralize that positive charge, and we would end up with our hydrogen on one and our bromine on the other. Okay, if it was H2O, that would attack. We would end up with water adding to that, and then what we would do is we would lose the proton here that would go back to the start of the reaction mechanism. Okay, and we would end up with an OH being added onto that carbon atom. So the previous reaction was a very simple symmetrical alkene, but we know that there are lots of alkenes out there that wouldn't be symmetrical. So if we have something which is an unsymmetrical alkene, so something like this, for example, okay, where we've only got one methyl group rather than two, then when we do our reaction with our H+, okay, so we're going to add our H+, okay, we're going to end up with two possible options. We can add the proton here, or we can add the proton here. Okay, so we have two possible options at this point. So how do we know which of these two products is going to be the correct one? Well, it goes back to our understanding from the material that Professor Osborne delivered about the stability of a carbocation. If you remember, she was talking about SN1 and SN2 reactions, and we talked about how in an SN1 reaction you lose the leaving group first and it forms a carbocation, but that will only happen if you have a stable carbocation. Well, the same principle applies here, that what we need is a stable carbocation. So we can see that in this first example here, we would have a primary carbocation. So if we were to continue the reaction mechanism, we would end up with this product. Okay, and in the bottom here, we have a secondary carbocation. Okay, so if we continue the reaction here, we would end up with this product. Okay, and what we know from the material that Professor Osborne talked about is that a secondary carbocation is more stable than a primary carbocation. So the preferred, the favoured product will be the one in red here. Okay, so this would be the product we would form. The product in black would be disfavoured and wouldn't be formed. So just to remind ourselves of why that is, remember that in a carbocation we have this hyperconjugation. So we have our carbon in the middle. Let's take a tertiary carbocation because that's one of the most stable ones. We can push electron density through these sigma bonds into that positive charge, and that helps to stabilize it. So in a tertiary carbocation, we have the ability to do that with 3 different carbon atoms. If we had a secondary carbocation, we can push electron density through 2 bonds. And if we have a primary carbocation like this, we can only do that through 1 bond. So therefore, the tertiary carbocation is more stable than the secondary, which is more stable than the primary. Okay, and so when we look back at that reaction we've just done, we can see that one option gave us a primary carbocation, the other option gave us a secondary carbocation. So therefore, the secondary carbocation would be more stable, and therefore that is the route that is more favoured. So this choice of carbon that we can attack with our electrophile leads us to a rule which helps us to remember or predict which product will result, and that's known as the Markovnikov rule. And what that states is that the hydrogen of your HX reagent, so the hydrogen is going to be the proton, that becomes attached to the carbon of the double bond that had more hydrogens attached to it in the alkene starting material. And again, we can understand why that is because if the carbon has more hydrogens attached to start with, then if we add another hydrogen to that, the opposite carbon in that double bond will end up being the more stable carbocation. So if we just look back at the example that we just looked at, we had the double bond here. So in this case, we have 1 hydrogen up here and we have 2 hydrogens here. When we do our reaction, we end up with 1 hydrogen here. We end up with 3 hydrogens here, and the positive charge sits there because this carbon up the top here is the one that's more substituted, and therefore it leads to the more stable carbocation. So we'll just go back and look at that Markovnikov rule now on the example that we just had. I've just shown you it for the final result, the favoured product, but let's just remind ourselves. We'll go right back and remember. Okay, here we go. We have our unsymmetrical alkene. We do our reaction and we end up with adding it either to the top one leaving our carbocation here, or we add to the bottom, leaving our carbocation here. And again, what we can see from this is we have a primary carbocation in this top root. In the bottom root we have the secondary carbocation, and therefore it's the bottom root that becomes the favoured one. We take our Br minus and we end up with our product here, where we have the Br added to that top one. Okay, so the Markovnikov rule shows us that the hydrogen will attach to the carbon of a double bond that had more hydrogens to start with, and the reason it does that is because by adding to that particular carbon it results in the more stable carbocation on the other carbon in that double bond.